Okay, this is a presentation about man-made polymers, or as we more commonly call them, plastics. You hear those terms, plastic, polymer. Well, polymer is just a fancy way of saying plastic. And it does a little bit more useful because plastic, as you've seen with metals, actually has a term for the plasticity of the ability of a plastic of a metal to stretch is called plastic. But they're general terms for man-made materials, and polymers is fancier. The um, One of the first plastics, man-made plastics, you'll hear more about some others in the podcast that accompany this module. Um, but one of the first was the result of a something like an X Prize. These kind of prizes are often done to improve, um, to have get inventors to invent stuff. You probably remember the X Prize for getting a human into space orbit, or into space. That was not a government agency. Um, Before that, there was a prize to somebody to be able to fly across the English Channel under human power. Um, well, back around the Civil War, there was a prize for somebody to come up with something as a replacement for billiard balls. Billiards have become very popular in the West and the saloons, and even then, in 1860s, they realized they couldn't rely on um, ivory because they were already killing too many elephants. Somebody came up with the idea of taking cellulose and soaking it with nitrate, and it would harden, and it became something kind of like a billiard ball. The problem is that this gun cotton, not because it's gun, it was the kind of cotton that you would put down into a musket. It was generally considered to be very fine. Um, there was no gunpowder with it, but if you soaked it with nitrate, it would harden, and you could shape it into billiard balls very carefully. Well, this cellulose nitrate also had a tendency to catch fire or to explode if it was heavily impacted. And there's a case where a saloon in the western states sent a bill to the billiard, sent an invoice to the billiard company to basically replace everything in their bar because a group of people were playing billiards and one of the billiard balls exploded, causing all of the guys who were playing poker to pull out their guns and start shooting up the place. And it all started because of an explosion of a billiard ball. Cellulose nitrate is also the material that old style movie films were made on. And it does not age well. There's been a lot of movies that were no longer being shown and just stored in warehouses, and they would open up the cases for them later and find that the films had just deteriorated, become a blob of liquid instead of the film that they could watch the movie with. Other stuff, history of plastics is perfect at figuring out what the um, necessity is the mother of invention. During the war, people wanted shoes, but the soldiers needed them more, so they came up with vinyl to be able to make shoes, nylon to make silk for stockings because the silk was being used for parachutes, A lot of that happens. Okay, what is in a plastic? Well, you have this polymer. A little bit about that in a second. You can also add fillers, put fibers in with it. You can also kind of commingle to some extent. Sometimes the commingling of polymers does not work, but sometimes it does. Okay, little bit of chemistry. We've seen some of this before, um, where carbon gets messed around with something else. Well, here it hooks up with hydrogen, and um, remember in how in steel making carbon was used to um, help get rid of the oxygen. Well, here when you're into this situation, you're taking um, petroleum feedstock um, or natural gas, which is lots of little carbons, and they're mixed with hydrogen, and you end up with a long chain of them. Um, and when you have the initial part, the ethane, and then you get ethylene monomer because you're now having it hooked to other ones, and then you get the polyethylene monomer or polyethylene chain. It's no longer a monomer. Monomer would just be one or two carbon um, atoms. When you get lots of carbon atoms together, you get these very long chains. And if it's just carbon and hydrogen, it's called polyethylene. These can have 20, 30 carbon atoms in them. And it's really, polyethylene is the most predominant plastic out there. It's what your plastic forks are made out of. But if you take that long chain of carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, and you throw in a chlorine in there, it now becomes polyvinyl chloride. And if you put in some nitrogen, you get nylon. And you still have these long chains, primarily polyethylene chains, but with little ends of them, perhaps, with nylon or with nitrogen that creates a nylon or chlorine attached to a carbon instead of a hydrogen, and then some stuff is attached to that. Um, you get an idea of how you get these other plastics. Um, it can get kind of complicated, and this isn't a class in chemistry, but how these chains go together um, and links, and you get the styrenes and the polypropylenes, um, and you'll notice one of the reasons for looking at this is you see at the top propane. That's the gas propane, and how it then becomes polypropylene because it's the natural order of propane, natural gases, and those is this carbon hydrogen chain. And how it's manipulated is what gives us plastics. Okay, now for the technology side of this. There are basically two types of plastics, man-made plastics. There's thermoplastics or thermosets. On the left side are the characteristics of thermoplastics. It smell, you can reuse them. Um, and it's you usually have these two-dimensional chains. More about that in a second. It's very handy stuff. You injection mold them, make bottles, water bottles, soda bottles, um, and then they're sent for recycling and remelted and used again. Thermosets, the characteristics over on the right side, is that it's a one-use. You set it up and you make your item, and you can't remelt it. It doesn't allow for that. And we'll get into the chain characteristics. Um, some examples of this are the plastic parts in your automobile engine. Um, engine gets hot. You don't want those plastics to melt. So all of those are thermo sets. And there's lots of other places where you see plastic that you know will be exposed to heat. You would use a thermoset. Now, looking at each of these categories briefly, you've got your thermoplastics like polyethylene, polypropylene, olefins, PVC, styrenes. Actually, Teflon, believe it or not, is a thermoplastic, but it has a very high melting point. But it is actually has the other characteristics. And you also have some other machinable plastics that can be thermoplastics. Now, how these things link is what makes one of the ways that plastics have different characteristics. One way is just the linear, that long chain of carbon-hydrate to carbon-hydrate to carbon-hydrate, nylon carbon-hydrate to carbon-hydrate. Running by itself is pretty simple. It just lays out there, and think of it as a a stick. There are other ones, and you saw a little bit of it when you had that slide that had the polystyrene. They start branching off, and when you get the chains branched like this, there's obviously going to be a little bit stronger. They're going to fit together, and they're going to get tangled up in each other. So you can have a higher density polyethylene that will be a little bit stronger because the chains are of a branched nature, and you can get networked linking, and that's where they actually really do connect to each other. The branch they just would lay together like a bunch of tree branches, but with networking they'd actually grow together and create some cross-linked branches in between there, and you would get an even ultra high density polyethylene. So summing up what I've been saying, you have a melt point. Now, each of these thermoplastics has a different melt point, and it just kind of depends on where what it is, and at room temperature, there'll be in these links. But when they get to this melt point, then those links will break down, those branches, and it'll fall apart, and they will be amorphous, be liquidy. And of course, when they cool off, they become hard again. And you can have low density, high density, and it depends on how it's manufactured, depends on that linkage. One very popular material out there these days is ultra high molecular weight polyethylene, the last thing on there, as opposed to low density polyethylene, which is the low density polyethylene is the bottles, plastic, silverware, whereas the ultra high molecular weight might be used for computer housings, things like that. And when you look at procurement part of this, so much more thermoplastics out there than there are thermosets. And so if you're designing something, you'll probably be able to get at some thermoplastics quite easily. Now the thermosets don't remelt, and they're hard, good insulators, and they generally have what are called chain linked um, structures. This is that fourth branching that I mentioned earlier. It was on the slide. Um, they actually will have some sort of knobs on the end of these that will hook them together, and that makes them very, very useful because they get to a lot of the things that you need to do. The common ones are generally phenolics. That's what the parts under your car, housings, on engine parts that still have distributors, small engines too, but all the other plastic parts that are inside the engine area of a car are going to be phenolics most likely. And it's also the type of material that's used for gluing plywood, making wafer board, those type of things. You've got some other ones. One important one for design people in engineering is the fluorinated polymers. And these are similar to Teflon, and they're really handy, really strong. You'll see them in use and designed into a lot of products. The epoxies are generally thermosets too, that you mix up and stir together. Um, the melamains, that's the plastic dishes actually. Um, and you can see that phenolics are very much a big part of it. Ureas are also glues for like contact cement and formica tabletops, countertops. Um, all of these various types of plastics. One other thing that you have to think about in terms of purchasing and how the industry works is there are commodity plastics and there are engineering plastics. And commodity plastics, a company will just be making lots of raw material to go out. And these generally go out in pellets or granules to the companies that will actually end up using them to melt them and make the products. But some of the plastic manufacturing companies do engineering plastics, and that is where they would do rolls or sheets, particularly for particular applications. If you think about the um, tablets or computer markets, they will actually make the material that will go to the computer manufacturer for the different components um, and designed in shape for that. And those are going to generally be PTFA, which is similar to Teflon, ultra high molecular weight polyethylene, some of these plastics that can be shaped or formed and quite often need to be formed before the end user or before the need to be performed by the plastics manufacturing chemical company before it goes to the manufacturer. This is kind of a crazy slide of all the commodity plastics, which is at the left 3/4 of it, um, where they'll make a polyethylene and just hope that somebody will buy it someday. Whereas a lot of the other styrenes and specific nylons and others are really made for engineering purposes. Little couple of last things here. There's also a different kind of man-made polymer um, called an elastomer. Now, there are natural rubbers, latexes, and if they're processed and vulcanize them, you make tires out of them. Um, but they're nowadays are more made out of Buna S. Um, elastomers are plastic. They stretch, but they return back to the normal shape. Rubber bands, that's actually the rubber, and that is a natural plastic. But there are others that have some of the stretchability and flexibility, and these are the elastomers. Um, Buna N is quite often used in O-rings, but that's another topic. And finally, there's are the silicon elastomers. Now that's the caulking and the um, glues, if you will, that you'll see in some stores, and that is a little bit unique. It actually, instead of having carbon chains, has silicon instead of carbon in there. And this is one of those things full of science fiction. Could there be life on another planet that's based on silicon rather than carbon? The reality is no, but it's always fun for science fiction buffs to think about it, because in this case, those silicon um, atoms fit the same bill as the carbon atoms in developing those long chains, and they can be rigid or flexible. And when I say these are inorganic, it's because organic chemistry is defined by having carbon in it. And so all of this plastic stuff is still part of organic chemistry, even though plastics are man-made. I'll mention something here um, about polymerization. You've experienced a little bit of it when you mix that material to house your metal piece um, that we're going to polish, and then you are basically doing an additive polymerization. You're mixing um, the initiator and the chain, and there's parts are put together, and you had to put in a drop that initiates the main resin that had all the chains in it, but that initiator, the few drops of liquid, caused the um, other chains to take shape into those specific shapes. You had um, there's some other ways that it's done. Some of them are very fascinating to look at. If you ever wanted to do some research exactly how the chemistry of this is scaled up to be major production is really quite fascinating. A lot of this stuff can be created in a laboratory, but then making it into the scale that you could actually ship products is quite different. Um, just understand the different ways polymerization takes place. One of the things that if you're ever developing, designing something, working with it, um, go to the websites of the people that make these things. I've had to call DuPont to get advice on how to get some film, some plastic films that we needed. Um, Very helpful people. They have chemists sitting around doing nothing, waiting to answer questions for you guys. And there's also a thing called MatWeb. I believe I've demonstrated it in class, and I'm probably going to put out a little exercise in how to use it. But it also tells you what is a great database for industrial materials.